Hello everyone. So for today's video, we will be discussing how to solve the random variable table, the discrete cumulative distribution function, and the probability mass function. So before everything else, let's read the problem. So a group of five friends are discussing the anime Bleach. We will label these friends B1, 2, 3, 4, and 5. Friends who watch Bleach are B1, 2, and 3, while friends B4 and B5 are not Bleach fans. Suppose that due to the limited resources, we can only take a sample of 3 friends. Assume that we will use simple random sampling without replacement to select our sample of size 3. We define X as number of friends who are bleach friends. Construct and solve for the following below. So before anything else, let's get our sample space first. So here in the right side, you can see our sample space. So with simple random sampling, we will get 10 samples. We will get 10 samples for our sample space. Now, note that we have defined our X as the number of friends who are Bleach fans. So, for solving the random variable table, we will define X as our random variable. Okay, and the values that the random variable take up will be your small x. Okay, so what will your big X, what values will your big X take up? So, for example, when we look at this sample right here, so B1, B2, and B3, we know that B1, we know that B1, B2, and B3 are all Bleach fans. So with that, um, the value of your big X will be 3. Okay, so there we go. Now, when we look at this one right here, this sample. So B1, B3, and B5, we know that B1 and B3 are beach fans. So there's only two, so your big X will have the value of 2. So now note, um, the values that your big X takes up will be your small x's. Okay, so these small x's will be very useful in assessing or in constructing our probability mass function. Okay, so before going into probability mass function, we must first note if our random variable is discrete or continuous. So we know that our random variable x can have the values 1, 2, and 3. As we have noted in our random variable table, right here, you can see there's 1, there's 2, and there's 3. So note that a random variable is discrete when um, the values that it takes up is either finite or countably finite. So we know that 1, 2, 3 are definitely finite numbers. So we know that x, our random variable, is discrete. Okay, so it's discrete. Now, as we move on, we shall solve for the probability mass function first. So, how do we solve for the probability mass function? Now, note that the probability mass function, uh, so let's write that down first. Let me see. So this is probability mass function. So we will label the table with x and the f of x. Okay. So now note, the probability mass function uses your small x. So again, what are the values of your small x? These are the values that your big X takes up. So that again is 1, 2, and 3. So let's put that down here in your probability mass function. So that's 1, 2, and 3. Now, um, what is your f of x? So in the probability mass function, we are trying to get the probability that a random variable is equal to a mass point, where your mass points are 1, 2, 3. So, again, we are checking the probability that the random variable is equal to the mass points. Now, for example, when we look at the mass point 1, okay, um, how many samples there that have that the random variable is equal to 1? So, we have 1, 2, 3. So that's 3. So um, we know that there's 3 out of 10 samples that have a value of the random variable equal to 1. So that's 3 out of 10. Now, when we look at the mass point as x is equal to 2, we have 1, 2, 3, 4, 5, 6. So that's 6. 6 over 10. And as we've seen earlier, there's only 1 for x equal to 3, so that's 1 over 10. Okay, so that's for your probability mass function. Next, we shall solve for the discrete cumulative distribution function, or the DCDF, or usually it's just CDF, but for certain terms we use DCDF. So first, when constructing our DCDF, note that the cumulative distribution function, we are checking the probability that the random variable is less than or equal to that mass point. So, okay, let me show you our DCDF first before I explain further. So we have 0, 3 over 10, 9 over 10, and 1. Okay, hold up for a moment. I will explain shortly. So right here, you can see that this is our cumulative distribution function. So why is it like that? So first, the cumulative distribution function checks the probability that your random variable is less than or equal to the mass point. Okay, so for example, let's just give an example. The probability that your random variable is less than or equal, sorry, is less than or equal to 1. Okay, so when we look at when we relate it to the probability mass function, it's easier to understand. So when we look at the probability that your random variable is less than or equal to 1, okay, it's basically adding up the probabilities that your mass point is equal to 0 and is equal to 1, because those are the natural numbers that are less than or equal to 1. So that's basically adding up your probability that your mass point is equal to 0 and your probability that your mass point is equal to 1. Okay, and we know we have no it's not defined, we don't have a probability for x equal to 0, so that's practically 0. Now for when your mass point is equal to 1, we know that's 3 over 10. Okay, so that's 3 over 10. Then you have 3 over 10. Now when you're um when we have when we're checking the probability that your random variable is less than or equal to 2, okay, um it's basically adding up your mass points that is equal to 0, equal to 1, and is equal to 2. So that's p x equal to 0, x equal to 1, x equal to 2. That's it. So that's 0 plus 3 over 10 plus 6 over 10 is equal to 9 over 10. Now, lastly, when you're looking for the probability that x is less than or equal to 3, that's basically x of 0, x of 1, x of 2, x of 3, x equal to 0. Sorry for using 1. So that's 0 plus 3 over 10 plus 6 over 10 plus 1 over 10. So that is equal to 1. Okay? So that's basically how you can view the cumulative distribution function. It's basically checks that if around the probability that your random variable is less than or equal to that max point. Okay, so that's for DCDF. Now, let us now move on into solving the problems under PMF and discrete cumulative distribution function. So first, we have for number 2a right here. So we have the event that there will be at most two bleach fans. So at most two bleach fans. So how do we write the probability of that? So that's P, K, where X is less than or equal to 2. So what? Again, we note that the event that there will be at most two bleach fans. So it's either two bleach fans or less than those two bleach fans. So we will write it as P, X is less than or equal to 2. Now, note, in this kind of form, this is the standard form for your cumulative distribution function, where it's P x less than or equal to some mass point here. Okay, some mass point there. Now, um, we are given that we're looking for the probability that x, your random variable, is less than or equal to 2. So, when we look at the piecewise function of your cumulative distribution function, we can see that less than or equal to 2 is inside this constraint, inside this range. So, um, we will note that its value is f, capital F of 2, because that's how we call the value for our cumulative distribution function. Contrary to that is we use the small f for our PMF. So again, coming back, we use the capital F, so f is equal to f of 2. Now, when we look at your piecewise function in your M21, f of 2 here is inside this constraint, so we just simply plug that value in. So 9 over 10. Okay, so that's how simple it is. Now, we have another problem here. So let's go for 2b. Okay, now here, the event that there will be more than one. Okay, so more than one bleach fan. So how do we write that? So the probability that there will be more than one bleach fan. So we're looking at um, the value where your random variable will have a value that is greater than 1. So let's just simply that x is greater than 1. Okay, so how do we write this in terms of the cumulative distribution function? So the complement of this function, the complement of this probability. So as we have noted in the past lectures at the start of Sat 5, that will be 1 minus p, where x is less than or equal to 1. Because as we know, if this is greater than, okay, then the complement of greater is less than or equal to, less than or equal. Okay, so that's just a bit of intuitive notion on the complement. So now we can write, because this is the standard form of your cumulative distribution function, then we can write it as 1 minus f of 1, capital F of 1, because again it's CDF. So when we look at f of 1, it goes inside this range. So we'll use the value 3 over 10. So here, that will be 1 minus 3 over 10, which is basically 7 over 10. Okay. Now for 2C, okay, 2C, okay. So here we have the event that there are at most three bleach fans and more than one bleach fan. So how do we write that? Okay, again, the event where there are at most three bleach fans. Okay, so how we wrote it here at 2a using the word at most. So we can write that initially as at most 3 bleach fans, okay, and it says there more than one bleach fan. So more than one. So more than one is like this. So 1 is less than x. Okay, so that's how you will write your probability. Now, how do we break this down? How can we write this down? So we can write this down in a manner of the following um, breaking down. Hold on. Okay. Let me explain why this works. So initially, you're looking at, for example, when you use the number line. Okay. So let's say this is 0, this is 3. So you're looking at the, okay, hold on, 1, 1, 2. For example, like that. You're looking at the value of the x where it is less than or equal to 3, but is greater than 1. Okay. So what does that look like? Um, Less than or equal to 3 is around here until 1. Okay, but there's a hole there, okay, because we are not including uh when x is equal to 1 itself. Now, how does this look like? How can we break that down into two separate probabilities where we are using the standard form of your cumulative distribution function, which is x is less than or equal to? So first, we know that we can write it as the probability that x is less than or equal to 3, because that takes up this whole um part. Okay, that's p x is less than or equal to 3. Now, how do we cut this part? How do we remove this part? Now, we can remove this part by stating that we are removing the probability that x is less than or equal to 1. Okay. So why does it need to be equal to 1? Because remember that our goal is that we do not include that x is equal to 1 here. Look at here, we don't have x equal to 1. So we will remove it. So we can see here that when we subtract p, the probability of x is less than or equal to 3, or the probability that and the probability that x is equal to 1, we get our desired probability. So that's basically it. So now we can continue solving using um, the concept of the discrete cumulative distribution function. So this will be f of f of 3 minus f of 1, where we can plug in the values. So we can see here that f of 3 is basically 1 right there. It's 1 minus, what's your f of 1? It's this, so that's 3 over 10. So that is basically 7 over 10. Okay. Now, for your probability mass function questions, let's start. So first we have for 3A, the event that there will be 3 bleach fans. Note that down. The event that there will be 3 bleach fans. So that's basically the probability that your random variable will be equal to 3. That's basically it. So how do we get this? Um, when we're dealing with the probability mass function, we just basically plug in um, uh, the value of your mass point. Okay, so when your random variable is equal to 3, so we can see here that in your probability mass function, its corresponding probability is 1 over 10. So let's input. First, we use the standard condition for probability mass function, which is f of 3, and then we've noted on the top here that it's 1 over 10. So that's 1 over 10. Okay. Now for 3b, we have here. the event that there will be no bleach fans. So no bleach fans is the probability that your random variable is equal to 0. So that is f of 0, since this is standard notation for PMF. And we note here that the mass point where x is equal to 0, then we have no probability for that. So that's basically 0. Okay. Now for 3C, okay, we have the event that there are less than 2 bleach fans. Okay. So how do we get that? So the event where there are less than 2 bleach fans. Okay. So right here, we will use the concept of limits to get the probability through the cumulative distribution function. So we know that less than 2 bleach fans is almost as similar as less than or equal to 2 bleach fans, but without the equal part. Okay, so it's almost as similar as the standard form of CDF, which is the P is the probability that x is less than or equal to 2. But we need to remove the equal to. Okay, so how do we do that? So I will introduce to you the concept of left limit here. So the notation for this is f is the f of 2 from the left. So why? When you look at the graph of your cumulative distribution function here, okay, so we are basically just graphing our piecewise function of the CDF here on the right side, okay? So here you can see that when we are looking for values that are less than 2, okay, so when you look at here, this is 2, right? This is 2, hold on. This is 2, this is your 2. Now, for here, when you're looking at the values from the left, okay, from the left, the limit from the left is 3 over 10. Sorry, this should be up here. Wait, I'm sorry, guys. This should be around here. There. Um, we are looking at values that okay, sorry. Um, when we look at values from the left of 2, okay, um, the our corresponding y value is 3 over 10. Okay, so you're looking at this side. Okay, but when x is less than or equal to 2, okay, so we are including this point. So we are looking at 9 over 10 in that case. Okay, so when p is less than or equal to 2, it's equal to 9 over 10. But when p is just less than 2, it's equal to 3 over 10. Okay, now that's with the concept of the left limit. Okay, now when we look at the left limit, we basically go one step down from our cumulative distribution function. So from 9 over 10, we go one step down. It's like a staircase. We go one step down to here, okay, to 3 over 10. So with that concept, okay, when we look at capital F of 2 from the left, so we look at f of 2, where its corresponding value is this. Then we just go one step down. One step down. There we go. It's 3 over 10. Okay. Let's just plug and play. And then that's f of 1. It's 3 over 10. See, we just go one step down. So why is it f of 1? Why is it f of 1? Because we just went one step down. Okay. This value corresponds to your f of 1, right? F of 1. Okay. So whenever you see this case where it is near the standard notation for your DCDF, but you need to remove the equal sign. So we can always use the concept of left limit for that specific um, value of the cumulative distribution function and just go one step down to change the notation. Okay, so let's move further for our last question here, 3D. So what is the probability of, sorry, um, the event that there are at most three bleach fans and at least one bleach fan? So three bleach fans are at most three and at least one. So we can write it down like this. Mhm. We write it down like this. So there at most three and at least one. So how do we break this down? We can break this down again in a manner using this concept right here, but I will not explain. I will explain further. Okay. So again, if we use this concept here from uh, right here, we're still using the concept where x is at most three. So we can still use this part because it takes the whole probability of 0 from 3. Now, the constraint here is at least 1. Okay? If it's at least 1, then we are now, instead of a whole with the red color here, we are now taking the whole part from 1 to 3. So, now, if we just want to remove this green part, right here, this green part, okay, we are removing the equal sign because we want to include that x is equal to 1 in your constraint. So we can break this down into the probability that your x is less than or equal to 3 minus the probability that your x is greater than 1. Your x is less than 1. Okay, so let's move on. Now, how do we break this out into the cumulative distribution function notation? So we know that this is the standard notation for your DCDF. So you can just write it as f is equal to f. You can write it as f3, and then now we see the similar case here. Here we see that similar case here. Okay, so we can just do the same notation where this will be um the standard rotation through the CDF for f of 1 from the left. Okay, from the left. Now, this will be f of 3 minus f of 0 is equal to 1 minus 0 is equal to 1. Okay, just to show you, f of 3 has the value of 1 right here. Then f of 0, you have 0, that will be 0. Okay, so for this last part, I will be discussing an alternative way. Instead of using the left limit approach right here, we will use a bit of a more complex and detailed approach or an intuitive approach on how we can solve your discrete cumulative distribution function. So for example, we have the question, um, for example, we have the question, what is the probability that your discrete cumulative distribution function is less than this specific mass point? So how can we break this down? Now, we know that um, through the discrete cumulative distribution function, intuitively, wait, for sorry, intuitively we know that the probability that your discrete cumulative distribution function is less than or equal to x is equal to the probability, okay, that um, your your discrete cumulative distribution function is less than x plus the probability that your big X is equal to x. Okay? Now, we are interested with this specific probability. So we isolate it. Now we transpose we transpose px is equal to x here on the other side. So we will have the probability that x is less than x is equal to the probability that your x is less than or equal to small x minus the probability that your x is equal to x. Okay, now um, after this, we can now solve it through the probability that your big X is less than X. And then note that this form is your discrete cumulative distribution function notation. So we can just note it as f of x. And then this is for the notation of your probability mass function. So that will be f of x. Okay, so that's it for a more complex approach. So first, we break it down into two probabilities, and then we isolate our desired probability, and then we convert um, the other side of the equation using the CDF and the PMF notations. So to add further, for we will now solve for the cumulative distribution function for continuous variables. So what is a continuous variable to start with? So earlier we discussed what is a discrete variable, that if it's finite or countably finite. So on the other hand, a continuous variable is a variable that is infinite or that is infinite. So for example, when we look at um, zero, the numbers between 0 and 1, okay, the number line, we can see that there are infinitely um, there are infinite um, numbers between them. So for example, I have like I I have 1/2 here. I have um, 1/4 here. I can have 0.99 here. I can have, for example, there 0.9999, 998, something like that. Then basically, you have an infinite number of um, possible numbers between 0 and 1. So that's an example of a continuous variable. So when we apply to here, okay, the properties of your cumulative distribution function would change when your variable is continuous compared to discrete. Okay, so right here, I have noted some notable properties with a cumulative distribution function when your variable is continuous. So here you have that the probability that your x is less than or equal to a is equal to just the probability that your x is less than a. Okay, where it is basically f of a. Okay, now here um, the probability. Okay, let's just skip that because it's the same thing. So here on the other hand, you have a form that basically says that p a uh, p where x is greater than a but is less than b is equal to just f of b minus f of a. Now, okay, that's also the same with um, when x is greater than or equal to. That's also the same with um, when x is less than or equal to b, but that's also the same as when x is less than or equal to a, but is greater than or equal to a, but is less than or equal to b. Okay, it's all the same. It's all the same. So how do we view this? So to illustrate, okay, you can imagine, um, for example, your function is this. Hold For example, your function is this. Oh, this there. Okay. Let's just say it's like that. For example, no. The function is like that. Okay, and then we're looking at. Let me just change it. We're looking at values from, let's say, um 0 to 1. Okay, let's put 1 here. 1. So when you look at that, let me just change the color for this. Hold on. Okay, I think we can work with that. So let me put some working for you guys to see better. So as you can see here, um, your the probability of this area right here, okay, is 1. Okay, that's 1. The the probability of this area is 1 because um that's the overall range of what we're looking at. Because remember, our only interest is between 0 and 1. Okay, 0 and 1. So when we look at this whole area, okay, like what is the probability of getting um less than, for example, less than one half? Okay, so you're gonna put something like that, and then you're gonna look at this area to get the probability that um your variable is less than one half. Now, what if it's like 3/4? What if it's 0.99? So you put it here, 0.99, then put some markings again. Then you're basically looking at this whole thing now to get the probability of 0.99. Okay, so note as well that for a cumulative distribution function that is continuous, okay, I forgot to note here as a number 4, let's put it here, that the probability that your continuous random variable is equal to a is 0, because you cannot have an area of just a line. Well, this is practically speaking, you cannot just have an area of what, like they say, um, what is the probability that x is equal to 3/4? No, because I'm just looking at a line. So um, a line doesn't have an area, so that's just basically 0. Okay, so that's just for illustration on how you want to look at your um your continuous cumulative distribution function. Okay, it basically um checks the area from the left. Okay, from the left of um the mass point that you're basing the value of your continuous random variable. So enough graphing. Let's try and solve some problems here. So here we are given the problem. Oh, I'm sorry, forgot to fix this. Sorry. Okay, so we are given the cumulative distribution function of your continuous random variable x with the following piecewise function. This. Okay. So f of x is equal to 1 if x is greater than 8. F of x is equal to 0.25x minus 0.75 when x is greater than or equal is less greater than or equal to 2 or is less than 8, while f of x is equal to 0 when your x is um, less than 2. Okay, so um, okay, let's try solving. So here we are asked what is the probability that your x is greater than or equal to 5. So first we can use some concepts of some tricks with the cumulative distribution function, but note again that that our standard form of our cumulative distribution function is p, okay, where the probability that your continuous variable is less than or equal to a. Okay, so we always want to arrive at this form so we can use the so we can always go back to f of a, because with with this we can now call the value of your the value from the piecewise function, so we can evaluate your probability. So right here we're given that the probability that your x is greater than or equal to 5. So we want to translate this probability into something that is less than or equal to. So let's try something. So first, we can get the complement of it. Okay, so that's 1 minus p um, x is less than 5. Okay, and then we have now, okay, we noted here from the property 1 that um, p the probability that x is less than a is also equal to the probability that x is less than or equal to a. So we can transform this into less than or equal to. So that's 1 minus the probability that your x is less than or equal to 5, and that's basically 1 minus f of 5, because we can now use your cumulative distribution function to evaluate the probability. So where does f of 5 fall? F of 5 falls right here at this specific constraint. Okay, so when we use that, that's basically 1 minus 0.25 times 5 minus 0.75. Okay, so if you have your calculators, just please evaluate it. I don't have mine, I'm very sorry. So yeah, that's basically it. Okay, so you can just evaluate this with your calculators and you'll get your answer for that probability. Okay, so here on the other hand, for letter B, okay, we can still use the concept of the discrete cumulative distribution function to break it down. So um what we still have here is the probability of your x being less than 6.5 minus the probability that your x is less than or equal to 4. Okay? But to be honest, it wouldn't matter what we put here, okay? As long as it's less than, because again, we have noted here that through the cumulative distribution function, okay, um, uh, when your continuous random variable is less than or equal to a, it's also equal to um, less than a. So that same applies when we're at greater than. So either way, even if you mistakenly put this or you remove this one, it wouldn't really matter because you're using a continuous random variable. Okay, so now we can clearly just evaluate this through f of 6.5 minus f of 4. So when we plug that in, we use this one, so that'll be 0.25 and 6.5 minus 0.75 minus 0.25 times 4 minus 0.75. Okay, so you can just use your calculators to evaluate. Thank you.